Good. How is the audio?
Hello? Test? Test? Can you hear me? Is there? Yeah. Test. Here, I think I can turn the volume up to... Is it louder now? What?
Test, 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 test.
Okay. You good? Alright.
Okay.
Yeah, I turned up the volume on it, so... Oh. Alright. There we go. Okay.
Should I
Start?
over?
I guess. Sure.
So this morning, many talks have covered why millimeter wave can play a very important role in 5G communication. Our project is trying to build a database for that, so that any points, 2 points of interest within the database on a map can be estimated in terms of what the path loss between them will be. So to start with, we started a measurement campaign. We focused on urban and suburban areas because there's just a very few measurement campaigns carried out for that environment, that kind of environment. We did that campaign on campus of UICT. It's in Annapolis.
Okay.
This is the setup for the measurement, but the key takeaway from this poster is figure. We used the ATU model the ATU version for line of sight case in suburban environments. That essentially gives us a great area. This distance for two. From the transmitter to the receiver. Essentially, this is a statistical model to estimate the path loss given the distance. And ATU model gives us a Gaussian type estimation. So here, the 3 schema range is shown here. But our data is collected on a continuous track here, and as we can see, the dotted results are what we received for the path loss. But because of the buildings, there are blockages, so the ATU 9% model won't be able to follow that trend really well. So we used another model called left edge diffraction model. It's basically one way to compute the offset for the path loss given the distance from the transmitter to the blockage point and from the blockage point to the receiver. And after the shift, as we can see, the dotted line is here. That's the shifted ATU model that follows our measurement really well.
For distance, you mean
Yes, that's right. Roughly speaking, you can put this graph like that. Roughly speaking, the distance from the transmitter to the receiver is increasing as we go from here to here. That's roughly like that.
And then you're just treating the building as a single knife edge right there in the middle. And that single knife edge feature follows the data much more.
Yes.
So you mean that in this part basically there is
This
part, and then again here.
This is diffracted.
This is here.
This is
You're well close here.
single knife edge diffracted region here, treating the building as a knife edge.
Yeah,
Which I'm kind of surprised that I don't know that you've shown me this graph yet, but
It's in the second paper.
oh, it's in the second
It's
paper.
the 2-page paper.
I didn't realize that had tracked quite that well. I didn't think that you could treat a building as a knife edge. I figured that we were going to have to treat it as some other geometric feature, but that tracks really well.
Yeah,
All things considered.
there are for sure. This one, because this one is blocked by the Michael's tower on the top roof.
Then we need to talk about doing a double knife edge model.
Oh, I see.
Yeah.
Interesting. Because you have two buildings.
Because we have two buildings, we have two knife edges.
Yes.
Yeah.
I think for this part, it does. This model does really well because.
Although, I mean, you're within the 3 sigma.
Yes.
Yeah.
That's the 3 sigma range.
And what are the different shifts of the same, almost the same curve? Like when you move to the next person. What are the
So what he's doing right now is the diagonal, but sorry, we're both talking. Sorry, but his new work is coming up a little the circular ray. He's going to come up with north, south, east, west, and the diagonals. And he's probably going to be looking at, he's going to have to stack, so it's going to be more of a packaging problem in terms of stacking up the layers.
Yeah, it depends on the distance, right?
Oh, he's already checked that out. Yeah. Tell him what you did here.
So yeah, there's a casing, right? Let's say there's like some kind of case, right? That might be there that needs to be taken into account. And we haven't done that.
Well, tell him what you did here with the chuck. Tell him what you did here
Oh
with
yeah,
the chuck.
so the chuck here,
So it's upside down here, obviously.
and so the chuck underneath kind of emulates that, right?
So there's
So it doesn't.
underneath that.
Yeah, but on probe stations, normally you have a metal chuck, so you're not going to put the antenna on the metal chuck. So he played around with, you can't see here in the picture, but he put a foam support. So the lid doesn't have to be that far. It doesn't really have to be that far.
Yeah, you want to make sure it's in the far field, and then so the foam is obviously there so that you don't short out the antenna, right? You can't have it metal directly on top of the antenna here because it's going to short it out, and then it's not going to radiate. So,
You could have a metal box farther away, but that'll be far enough away.
yeah, you want to make sure it does affect, the way it looks.
Yeah, you can.
We've submitted this work for publication, and in a year or so, we're less than a year, maybe like 2 months.
Well, the one paper is going to come out. The antenna part, the antenna layer was already, that one's just not published, it's going to be published. But then he's talking about the beam forms, and then new work that we're being funded all the time.
Hello. We're live streaming on YouTube. Would you mind giving us a short?
This poster is about vehicular communication over millimeter waves. The main idea is that the traditional technologies such as DSRC or LTE will likely support the requirements of next generation vehicular systems in terms of data rates. So what we try to see is that if millimeter waves are actually good for meeting these requirements. And we developed a stochastical model for the coverage and the connectivity probabilities of the nodes. And our main results show that there exists a trade-off between the beam width of the system, of the beams that can be steered, the periodicity of the tracking, because the nodes, in order to exploit millimeter wave frequencies, needs to be aligned. And so there is a trade-off with the alignment periodicity and also with the speed of vehicles. And our main result is that there exists a density threshold of base stations that are deployed on highways, for instance, saying that for low densities it is more likely to use very narrow beams in order to increase the range that can be discovered by base stations, while in order to increase the coverage range of each base station, when increasing the density, we may also leverage on wider beams. So this is the trade-off, and of course the throughput results are follow this same rationale of our first preliminary results.
All right, cool.
Thank you.
Thanks.
Traditional kind of like, if you think about millimeter wave beams, we think about them being very directional, like pencil-like beams. But what we see in practice is that even this X60 platform or even the CAT hardware off-the-shelf devices, so recent papers have actually measured the beam patterns in the anechoic chambers, let's say, and they look like all over the place, kind of similar to what we have here. You have a main beam and then you have a lot of side beams. So we ask these questions like, do we need to rethink this beam training procedure, whether it's like, for example, the question of finding the perfect, the ideal.
What's the scale here? I mean, is it, I guess it's
right.
10 dB, so these are like 10, 20 dB down.
Yeah, so beam would be around 25 to 25 degrees, and that's with a 24 element array. Yeah. So, and then if you look at the range that we are getting, it's like almost 25 meters. We were still getting multi-GPS rates. So it's not really like, you cannot go far if you have this wide beam. So you have a wide
So
beam.
explain this to me. At 5 meter distance, what is this applying?
Right. So this is a color map. First of all, it shows you SNR.
Okay, got
so
it. Hotter.
Hotter is like
Right.
yellow is better. Right. So here we have AP or transmit 5 beams. We have 25 beams from -12 to 12. So
Okay, so these spatial. These are not spatial positions.
No. So these are the angular directions of the beam. So we can steer the beam from, let's say, -60 degrees all the way to 60 degrees.
Okay, so the beam index corresponds to its angle of path.
Yes. We have some elevation beams as well, like they are different elevation, but they are not perfectly steerable. So this is steering in azimuth along the transmit side and the receive side. So here the center would be the beam index 00, so that's your center beam. And for a free space line of sight propagation, you should get maximum here.
So you're only a few dB down here, 5 dB down here.
Yeah, so this is a corridor environment. So you have like a reflector.
You're getting waveguide from the walls.
Yeah, walls. Yeah. So what we see here is the reason is that first of all you have these side lobes and reflection from the wall. So the side lobes are strong enough to give you gigabit per second rates and high enough SNR. And then what we also see is that if you think about the first order reflections, so the angular separation between the line of sight path and that first order reflection, it is such that you have some side beams which are getting those reflected parts. But what we see as we move away from the transmitter, here it's
the angle of arrival
25.
increases too.
So it's mostly like, even if you're getting the reflection, it's kind of like...
Yeah, the angle of arrival is...
Right, yeah.
Well,
So
here's the question. Are you going to model that analytically, like with ray tracing or something?
right, so we have currently an extension of this work where we are actually mapping the environment and doing exactly that. Ray tracing, comparing it with existing models from, let's say, Rappaport and others. So that's an extension. Another interesting result what we saw is here we are comparing the performance with line of sight and then just the reflected part. So here we have actually the phase area pointing towards a strong reflector, which here in this case is a white pole. So we see that we are almost getting the same throughput. The range is not long enough, but it's like a conference room environment. So within that environment, we are getting almost the same rates.
Yeah, that's interesting. People have been doing that at terahertz frequencies too.
Right.
Because otherwise, you use the line of sight length, you're dead.
Yeah, but this kind of gives us the notion of 60 gigahertz communication is not that vulnerable, you can say.
Well, exactly.
It has some...
Well, right, you got to steer. If the line of sight gets blocked, you steer to the whiteboard.
Right. But it is manageable in the indoor environment. And then finally, we also ask this question of so does mobility still matter? If we are getting these kind of beam patterns and overlap, so these kind of systems, does it still matter that beam steering is required? And if we are locked on to some suboptimal beam, then what is the hit we are getting in terms of not adopting? So here we are asking those questions. So you can see this is the optimal adaptation, so you adopt both sides perfectly. And then this is only the receive side, and then there is no adaptation here. So we get to see that even with this wide kind of beam width and overlap and side lobes, there is still value to doing adaptation. Because if you don't adapt, you are going to
even at one
that
end, you get most of it from just doing it at one end.
Right, so that's another takeaway message, that even if only one side is smart, whether it's the transmitter or the receiver, one side is adaptive.
Oh, so you're requiring Wi-Fi?
Sure. So to
And our host. Could you restart the software?
In the presentation. And then it uses a wide
Okay.
transmission, and then it's called
Yeah, for some reason it just.
Did you know Carl Dietrich? Oh, yeah. Oh, but just, I don't need
You can move closer.
Have a hybrid system with, let's say electrical part as well as optical part. So here everything we do is optical part and the black is electrical. So one scenario is that...
Hello. We're live streaming on YouTube. Do you want to give a short presentation of your poster?
Poster, I'm looking for a person.
Oh, all right.
So I have something.
and you can route it long distance. So several meters, so it could be very good for different access points, smaller people. And this is all low cost because they're using CMOS.
You want to do like of each thing poster? So.
This one scenario, many such scenarios. Other is at the receive side. If I could modulate optical laser with RSC, this optical filter can be widely common. There are some challenges in this architecture, but you can make flexible filters at millimeter wave because it's flexible. And there are many such other beamforming others. So the critical block is this modulator, which is RF to optical modulator, because it has a large amount of non-linearity if you get So we are looking at techniques by which we can linearize it, make it more linear, so that it's suitable for analog modulation. So classical optics was being done using discrete structures. Right now,
So you're going to have to use this concept of very but being that everything into having more than one user sending in the same room simultaneously, and how we can use the propagation awareness and scheduling.
You said you work on device-to-device communication.
Yeah, from an edge model. Try to see
how maximum
try to see how
and it's about 2 millimeter long. But again, it has every amount of non-linearity. Not so long, so you have energy issues on high frequency. We are looking at very complex modulators based upon ring modulators. And these are very complex. You see them like a dot here. Again, the issue is they have non-linearity. So we're looking at structures like differential structures where we can make them we get rid of even order non-linearity. Then there are some ideas where this ring, if wires inserted, we can give expansive response, like super linear. Max engine response is non-linear and come up with schemes where you combine them with high linearity. We have seen linearity go up better than 10 dB. CPR about in excess of 100 dB, which is sufficient, which is what folks look for. So this way you can carry RF on fiber and it opens a lot of different possibilities.
Not following me.
Sorry.
That's part of work.
Each relay we put what? We combine.
Yeah. So I only hear I tried working on that.
How to make the decision how much to buy. I mean, this is really one of the things what you were saying about that coding. I can see how
No, we work
what
on
you were
hybrid
saying.
microcontroller. I also work on hybrid.
Like combine several flows. You're saying
It won't be just two flows, it may be combined like modules.
yeah, after
Need a meter.
Right, like, yeah, like yeah.
and the
Yeah, so
this guy combines several flows. This guy they combine together. See?
yeah.
and also it should be able
Like
to
our
perform
yeah. Depends on state schedule to control the forwarding.
So again, what is different?
This is illustration of the
What is different just compared to previous approach that was linear
They combine the packets at the first part. It's called intraflow. Here it's interflow. Because like right, because
There I have
when packets are uncoupled, it makes the loads come back to the flow. Because there is
But this is more difficult to shift, right? If you put many flows together, then you might lose all of them, right?
What's
but there are multiple flows. They are flows. Make this one not like packet. Usually, traditional method, they combine packets on the same which is uncouplable. Yeah. Right.
what we suggest is that if we have a if we have a phase array with so for a traditional phase array, basically you have a static beam pattern of each element and you change the phase across each of the elements to shape the beam. So we are saying that if we could have some tunability, some reconfigurability of a single element, we can focus the beam on plus minus 45 degree and also broadside. In a non-line of sight operation, we could increase the SNR from 5.5 dB to 12.5 dB, which is very significant. And also, even in a line of sight operation, we can even get marginal improvement because, for example, if we want to transmit at 45 degrees, we can focus most of the power at that particular angle compared to a traditional phase power. So here's our concept of a reconfigurable element. So traditionally, that's what you have for a static antenna. You have a fixed beam pattern, which you can see if you want to transmit to a 60-degree angle, the directivity drops by 14 dB, and we know that the phased array pattern is basically the element pattern multiplied by the array pattern. So if the element pattern performs pretty bad at 60 degrees, you won't get a good result, even if you use the phased array. Right now, if we introduce some tunability of each of the elements to focus the beam at plus 45 and minus 45 degrees, and then use the traditional phased array technique, so that at 60 degrees you get a minus 0.9 dB rather than minus 14 dB, which is very strong improvement. And we know that antennas use the same method that we use for the transmitter to the receiver side. This is the antenna structure that we used, and those are the HFSS simulation of the radiation. That this antenna system generates. So we put 40 gigahertz and 70 gigahertz just to show that across the frequency band we can always get beam shaping into wide range angle of the arrival. So for 40 gigahertz, if we want the beam to be broadside, we have the middle port, and if we want the beam to be, say, 45 degrees, we have one of the middle port and one of the side ports. It's a little bit different in 70 gigahertz, in which we have one of the side ports to modify the degree beam pattern. And interestingly, if you have two side ports simultaneously, those two signals can be independent.
Okay.
So this is the chip photo and the architecture that we designed. Each of the chip takes a 3mm by 2mm. It's controlled by a 4-stage millimeter wave DAC PA, which provides the changing of impedance at the ports to change the current distribution on the surface, and thus the radiation pattern. And here's the packaging of the chip. So we placed this chip in the middle of the
wireless PC, and all the high frequency allo signals is going through SMT connector on-chip logic transmission.
Let's go there first.
Hello. We're live streaming on YouTube. Would you mind giving us a short presentation on your poster?
Sure. In this study, I'm studying the impact of diffuse scattering for millimeter wave channel modeling. So this is a rough surface, and we study using the imperial equation method that at millimeter wave frequencies, diffuse component becomes comparable and even exceeds from the reflected power. Therefore, we have to include the impact of diffuse scattering in our millimeter wave channel model. And here I show that in our ray tracing model we use Kirchhoff approximation to implement the impact of diffuse scattering. These are 20 by 20 tiles. Each one is 10 times the correlation length of the surface roughness, which are placed around the specular component to include the impact of diffuse scattering. And here is the geometry we have considered, which is an urban canyon. So we have asphalt for the road and cement for basically concrete for the buildings. And we have considered both isotropic and directional antennas at transmitter and receiver side, and calculated the path loss, the coherence, the coverage distance, and the spatial correlation for 1D and 2D antenna arrays. Here, the coverage distance that they aim to get is 200 meters. Here, I have basically plotted the combined gain that is required to achieve this 200 meter coverage distance, and concluded that we can achieve 200 meter coverage distance using a reasonable combined gain at the transmitter and receiver in the millimeter wave range. And these are two antenna elements which are placed horizontally in these figures and placed vertically in these figures, and it shows that our azimuth spatial correlation drops much faster than our elevation spatial correlation. And this is for the 2D antenna array, in which one element is at the center of the square and the rest the second element is placed at 1 millimeter increments from the first element in a 20 by 20 square. And this is the 2D spatial correlation. Here we have the reference plot. In each subsequent plot we change only one of the parameters to basically study the impact of that single parameter. So here we see that, for example, using directional antennas, we get larger correlations compared to using isotropic antennas. Or, for example, here we see that at 300 gigahertz, we get here a smaller spatial correlation compared to 60 gigahertz. And these are the main results for this study.
Cool.
Thank you.
Thanks.
So what next?
I guess that's it.